Second. All right, welcome everybody. We'll go ahead and get started.
Tried to do that with music before. It just wasn't very well.
Second, JWST informational lunch. And we are very pleased today. We have Marcia Rieke on the phone. She's going to be talking about NIRCam. She's the NIRCam PI. I had the pleasure of meeting Marcia back at the postdoc on this month. So one of the people I look up to most in the infrared universe. So Marcia, I think you can take it away.
Okay. So, NIRCam is a quite complicated camera, and there are many reasons why it costs a lot more than Spitzer instruments, and you'll soon appreciate that as I go through this talk. Of course, NIRCam is the 0.6 to 5 micron camera for JWST, and there are a number of unique features that NIRCam has, some of which are similar to IRAC, some of which are quite different. One way where it's similar to IRAC is that it has a refractive design which helps make it small, and this lineup of instruments, NIRCam is the eeny-weeny one. We're the smallest instrument, even though we're the central short wavelength imager. And I'll go through some of the other characteristics here. NIRCam employs a dichroic, so you can observe, again, a commonality with IRAC. So you can observe the sky at 2 wavelengths at once, which helps improve survey efficiency, and also makes for better Nyquist sampling because we can have different pixel scales for the short wavelength arm and the long wavelength arm. And see also that we have coronagraphic capability for both short and long wavelengths. And I'll go over some of the issues with how you use that coronagraph. Another very unique property of NIRCam is that it's the facility wavefront sensor, meaning that you take images with NIRCam and derive corrections to the 18 mirror segments to keep the telescope fully aligned. Because the facility wavefront.
Marcia, hear us?
Yes, I can.
Can you speak closer to whatever speaker microphone that's picking up your voice?
Okay. Hopefully better.
Yes, it is. Thank you. Thank you.
So by virtue of the fact that NIRCam is the wavefront sensor, it has to be fully redundant because it can't fail. And so the way we have designed it is that it's actually 2 copies of a camera mounted back to back. And so that's how we achieve the full redundancy. And from the science perspective, this means that one gets double the field of view for surveys because we can use both halves of science. And you'll also see that we have dual filter pupil wheels so that we have enough slots to accommodate some of the wavefront sensing hardware. And there's also a pupil imaging lens to check optical alignment of particularly short wavelength arm that does the wavefront sensing. Right now at Goddard, it's already mounted in the ISIM, which is the Integrated Science Instrument Module. And if you look in the lower right of this slide, you'll see a kind of black structure. That's the actual ISIM, and it holds all the instruments together. And then that whole structure with the instruments will get mounted on the back of the telescope. NIRCam is the one in the center. And the ISIM is just now coming out of the chamber that you see in the upper right, which is called the SES, or Space Environment Simulator, which is a huge cryo chamber and had both the ISIM and instruments and a very elaborate telescope simulator all inside it for a big round of cryo tests. You can this chamber by looking at the consoles down here. You can see a picture of NIRCam in the lower left before it got mounted in, and there's in a line.
Hey, Marcia?
Yeah.
We had some technical difficulties over here. We had some really bad ringing feedback for a little bit.
Okay.
So we lost you probably at the beginning of this slide.
Okay. So you can see where the light comes in, and one half NIRCam. So there are these. So the light comes into this focus and alignment mechanism, and that allows us to align the NIRCam pupil with the telescope pupil, which is quite important for wavefront sensing. And you can see the light comes up to the lenses. There's the dichroic that splits it into the short wavelength arm and the long wavelength arm. And this particular computed drawing version of NIRCam includes the pupil imaging lens in the deployed state. It's usually out of the beam. It has a very strong spring on it so that it can't fail in the beam. This is called the PI spring, for reasons you guys can guess. You'll notice that the two detector packages are different size. The short wavelength one is 4 2K by 2Ks, and the long wavelength is just 1, which has to do with keeping the pixel scale matched to the Nyquist sampling for the long and short wave, and I'll come to the pixel scale in a moment. Here I superposed the real NIRCam onto that drawing, and you can see the two big filter wheels, the pupil imaging lens under this big cover, the two detectors, and pickoff mirror is wrapped up because it's so exposed and we don't want stuff to get on it. I'll go over the behavior of the two channels a bit more. So you can see module A, module B, meaning the A is one half, B is the identical other half, and then each one has a short wavelength and a long wavelength channel that are the same pieces of sky. And you see the pixel scales, and so one of the design rationales for JWST was to give spatial sampling at 2 microns like one gets with HST in the visible, and you can see from these pixel scales that we achieved that. And you can also see that the field of view is just over 2 arc minutes on a side. So the field of view grand total is sort of 2.2 by 4.4 arc minutes. These gaps between the short wavelength chips are about 6 arc seconds, and the two modules are separated by about 40 arc seconds. Vectors are NIRCam telluride arrays, and NIRCam has a total of 10 of them, and the performance is just fabulous. The read noises that you see over in this table are in 1,000 seconds, which is what we're baselining is the nominal length for a single exposure, and then one would dither and take however many 1,000-second exposures one needed for a survey. And of course, one can take much shorter exposures. Full frame, your shortest exposure is 10.6 seconds, and because of having to reset the pixels, you actually have to spend 21 seconds. So, but these arrays can be read out in a variety of subarray modes. I'll describe that more when we come to transits, and that's important for looking at bright sources. Here's a little bit about how NIRCam works as a wavefront sensor, and in very schematic form here is showing what happens after launch. We first turn on and we'll see 18 dots of light, one star per primary mirror segment. There'll be a procedure to identify all these 18 images and then arrange them into a sequence that's logical given the naming conventions and locations. And then to start reaching the final image, one has to first take focus differences between pairs of images. We've done with something called the dispersed Hartman sensor. So here in pink, you see the pupil of the telescope, and in purple, you see little rectangles that are actually filled with, each one of these rectangles has a grism and a wedge, and when you take an image of a star, you'll get a total of 10 spectra, and there are two sets of these dispersed Hartmann sensors so that you get all 18 segments and overlaps, so you can think of it as something similar to radio telescope phase closure. And you'll notice that the star turns into these things that look like barber poles, and by measuring the frequency of this variation in the spectrum, you can tell how much out of phase or how much defocus there is between two segments. After this procedure, then one goes on to what we call fine phasing, where things aren't quite perfectly lined up. And there are some weak lenses in NIRCam that take in and out of focus images that then get you to the fully aligned state. And this last step uses algorithms that are very similar to what are used for ground-based adaptive optics control. So this whole dispersed Hartmann sensor business has been tested on the Keck, and fine phasing part, of course, has been tested many, many times by AO groups around the world. So there's no concern about anything in this. Even though it's complicated, this is pretty straightforward given what people do now at a couple of kilohertz on the ground, and we're only going to have to do every 2 weeks this last step, keep the telescope perfectly lined up. Here are samples of data taken during this last cryo test. This colorful picture shows a picture of the telescope simulator pupil, which is subdivided into the segments. These funny holes in the pupil are not representative of JWST, but rather part of the telescope simulator that allowed it to have a pupil viewer, so those aren't going to be the real thing. And you can see the inputs for these dispersed Hartmann sensors, and what we're doing in this alignment check was making certain that only two segments contribute to any one of these rectangular openings with its prism and wedge. And we're able to achieve that by adjusting our focus adjustment mechanism.
Hey, Marcia?
Yeah.
We're having trouble hearing again. Would it be possible to... Yeah, sorry.
I'll stay close. So did you hear part about the dispersed Hartmann sensor here?
Yeah.
Okay. So and then these other images are in focus and out of focus images using the weak lenses that are built into NIRCam, and these are in the pupil wheel, so we don't have to adjust the secondary mirror. We take a sequence of images like this. They will be sent to the ground, processed, corrections to the primary mirror segments derived, and then those will be sent back up to the telescope, and the segments will be moved. So there's none of this wavefront sensing calculation is done on orbit, just taking the images and then, of course, moving the mirror segments themselves. The key of NIRCam is its collection of filters, and we have three types of filters. We have wide, medium, narrow, and the filters have names that indicate 100 times the central wavelength and whether it's wide, medium, or narrow. And in this graphic here, this black band, oops, sorry about that. The black band is the dichroic deadband, and you can see the selection of filters. And a lot more filters than I had originally envisioned, but I think most of them are going to be put to really good use, as you'll see. And this bottom plot shows that the W filters, all of the filters actually have great transmission, but the W filters in particular are excellent, excellent filters. This is just a schematic representation of some of the medium band filters overlaid onto various ices that one might find either on ice grains in interstellar medium or on debris disks or on outer solar system bodies. And so NIRCam will be useful for getting diagnostic information on ices and also on possible features in brown dwarfs. I'll come back to that when I talk about the science program. The NIRCam coronagraph operates in a, let's say, non-standard fashion. And the rationale for this is that we didn't want to cut off any of the potential field of view for deep surveys. And so to use the coronagraph, one has to rotate the pupil wheel to a special position that has a Leo stop with a wedge that deflects the beam, and there is a mask that is ordinarily just outside the field of view. And when you rotate to the correct wedge position, that wedge deflects the image so that the coronagraphic masks fall onto the FPA. And this slide shows that there are two flavors of Leo stops, one for the spot occulters and one for wedge. These were designed by folks up at JPL, and John Christ played a big role in getting these laid out. Their throughput is rather low, just under 20%. But you'll notice that the plan is to avoid any of these nasty diffracting surfaces. So we've given up some sensitivity in favor of reducing diffracted light, because an 18-segment telescope isn't really what one would choose for an optimum coronagraph. But by making this choice, we can do pretty well. The picture on the right shows actually a short wavelength field of view with arranged more or less spatially correctly, with the mask as seen by that short wavelength field of view. And of course, for the length, the coronagraphic mask looks like it's split in two. For the long wavelengths, of course, it looks like a solid piece, and this one mask in the center is one of the primary masks for the long wavelengths, and so it's okay that it's close to an edge in the short waves because it's big enough that you would not want to use it for short wavelengths. You can also see in this image what we call the bar, or sometimes called wedge occulters, where the width of the occulter varies with position along it, and that way you can find an optimum width for whatever wavelength filter might be choosing to use. The spot filters, there's one short wavelength spot that's optimized for 2.1 microns, with the thought being it would be used for water ice, and then the other two spots are for 3.35 and 4.3 microns. These squares are neutral density spots that are used for target acquisition, and this curve over here shows that they're sort of neutral density. They're not totally neutral. They're more effective at they're higher optical density at short wavelength and then drop off as you go to longer wavelengths. But of course, that's the same way in which the stellar flux will be dropping, so that's not too big an issue. So operationally, one would go to your target star, put it in one of these spots. There'll be an acquisition routine to get it centered up, and then during it checkout, we will have calibrated offsets from the centers of the squares to the various features. This performance of the 2.1 micron spot, the only short wavelength spot, and this was computed by John Christ. We expect better contrast ratios at longer wavelengths, And if you just took a single image, this black line called untracked is the kind of suppression that you would get. And looking at using JWST in a fashion similar to what one does with HST, take an image, rotate, take another image, and difference to get rid of some of the, whoops, my mouse too jumpy, get rid of scattered light artifacts. And the telescope might drift a little bit in its alignment in between those two images, and that's what these different curves are. And now we're conservatively estimating that there'll be of order 5 nanometers wavefront error change between the two images, so that corresponds to this curve here. To improve coronography that people at Space Telescope Science Institute have been looking at is a scheme where you would do very small millisecond dithers on a small grid. Some patterns are shown here, so that one can compensate for the fact that you can't roll quite as much with JWST as HST. And these plots, the bottom one is the easiest one to look at here. You can get a gain in contrast of factors of roughly 5 by doing these small dithers on a grid. And so I'm sure we're going to check this all out when we're executing commissioning, and we'll be able to give users advice on what's the best way to do this. But Remy Sumer and the group at the Institute have done a lot of work at trying to figure out how to use a telescope that really is not optimum for coronography, but how to use it for good effect. Okay, now that you are somewhat familiar with the hardware, I'm going to talk some now about what style one might use NIRCam for. And
Hey, Marcia?
yeah.
We're having trouble again, I'm sorry.
Okay, try not to swallow the phone.
Sorry, thank you.
There are 4 science themes that JWST's performance is benchmarked against. Looking for the first light in the universe, which one really ought to think of as the first stellar agglomerations. Period of galaxy assembly, which you can think of as how galaxy clusters grow, how the Hubble sequence gets established, and so on. Stars and solar systems, which to my team largely means studying star formation, and then exoplanets, and possibly shed light on conditions for life. And in each of these, I show in red some of the things that NIRCam will do towards achieving the science goals of these 4 themes. And these 4 themes were established, around the year 2000, and they've stayed robust. But I do have to say that the 4th one, exoplanets and so on, has obviously grown tremendously in importance relative to when we were first thinking about this telescope. My team had to write a proposal that in 2002 to get selected to build NIRCam, and we lumped all of the extragalactic programs we would do into one bunch. And then we had a star formation program and a debris disk and exoplanet program, and we included some solar system topics in this as well. And you'll notice that there's some things here labeled TF. That stands for tunable filter, which was going to be a Canadian contribution to NIRCam, but quickly got changed when the project really got moving. The Canadians split their own, got their own instrument, which is now called NIRIS, which unfortunately does not have a tunable filter in it anymore because there were technical difficulties, but they found some very good things to take its place. And NIRCam got some GRISMs for its long wavelength arm. Originally, these were to be used for wavefront sensing, but now look like they may be a real workhorse tool for exoplanet transit spectroscopy. So the NIRCam team extragalactic program is one where a lot of emphasis will be put on trying to find when galaxies really started forming in appreciable numbers, trying to find, objects at redshifts higher than what HST has found, and our exact survey program is being developed right now, but we are, and I'll show a trial set of thoughts we have on how we would actually lay out one of our surveys. We're thinking that the UDF and part of the UDF and part of HDF North would be our prime targets, 2 places, so that regardless of launch date, we have something that we would be able to observe quickly and have some robustness against cosmic variance. We're going to be doing this program in collaboration with the NIRSpec team, so that NIRCam Team Tom will be used for the imaging part, and we're working toward a plan where all of the instrument teams would basically observe the same pieces of sky, and that way we leave as much for everyone else as possible instead of each team take one part of, say, the UDF, and that means that one couldn't do a complete program as a Joe. So we're trying to leave as much territory as we can for everyone else. And the survey questions won't surprise anybody. We'd like to know things about luminosity functions, surface brightness distributions, how is the star formation spread out over the galaxy. In terms of luminosity functions, we're very interested in numbers of low luminosity UV emitters. Can we learn about reionization by finding these? Can we find out anything about the relationship of high redshift black holes to nascent galaxies and so on? And one of in this program is, I'm not trying to badmouth with C3IR on HST, but just to show you graphically what improvement you get at, this is now a comparison at 1.6 microns, by going to the bigger telescope. And that's one of the whole points here, that instead of getting a slightly fuzzy image, we're really going to be able to get some detail at these infrared wavelengths. And these other plots to the left show, as a function of redshift, how many pixels you get per kiloparsec, and that we actually have the sensitivity to detect bulges from disks. So particularly in the galaxy assembly program, thinking of sort of Z of 2 to 7, HST is given as samples of galaxies there, but this is where we're really going to begin to understand structures, the development of structure, and so on. And the fact that we're going to have full near-infrared coverage with high spatial resolution is really going to be a game changer. I mean, this plot of different galaxy imagers, and and I'm not trying to make some instrument look bad, but we all know that IRAC on Spitzer is a camera, but on an 85 centimeter telescope, and the diffraction limit is such that, I gotta be careful with my mouse, is such that you just don't get much spatial information. And now, with JWST and NIRCam, we'll be able to have images that go across this whole wavelength region with great detail and great sensitivity. And I think people need to be folding into their thinking what it means to have all of these wavelengths and how that will help photosynthesis and all of that kind of stuff. So the NIRCam team sample program, you can see this figure on the left where we've got what are essentially two adjacent NIRCam fields of view, and there's some dither patterns involved here, and there's central stripes where each filter, wide filter, would get 75,000 seconds, and these adjacent regions would get half that amount. And in the chart here are listed the filters that we would use, and because there are more short wavelength than long wavelength filters, at one time we had doubled the exposure time on 444W, but what we're going to do now, and I see I've made a mistake on this chart, these two actually will get the same 75 kiloseconds. I'm not splitting it between them. And so these values will be √2 better. But we discovered when we started thinking about this in detail that this medium band filter, because it doesn't pick up so much of the zodiacal background, actually has the same continuum sensitivity as the broader filter. So if you take images in each of these, you can get significantly better Z discrimination. The Z of 5 galaxy shows where H alpha would be just getting into this 4.1 micron filter. And you can think about the fact that at higher redshift, at Z of 9 and greater, the Balmer break would be moving through this filter, and you'll be able to get quite accurate photo Zs from that feature alone. So this is the kind of program that we're looking at. And just to emphasize some more about the Balmer break, of course, this is where some of the IRAC detections of the HST galaxies has played a big role in proving that there's an old, well, not old, but not super young stellar population. And I think this kind of scheme of looking at this Balmer break is going to play quite an important role in the JWST extragalactic program. And those of you that have been following some of the work on high redshift galaxies using HST and Spitzer, Dan Stark, who's here in Arizona, has done a lot of work at looking at how the IRAC colors have been somewhat distorted, shall we say, by strong emission lines. And this plot shows you how different emission lines trace through the NIRCam filters at different redshifts. And I think as we think about our photo Zs and our ability to select targets for follow-up spectroscopy with NIRSpec, we're going to have to think very carefully about the effect of strong emission lines at high redshift, because there's plenty of evidence that indeed the lines are quite strong as we get above Z of 5. Okay, let me go to another one of our team programs, and that is what we're thinking about doing in the star formation arena. And the kinds of questions we would like to ask are getting a better understanding of the cloud core collapse process. How do, what variables influence the initial mass function? How do disks evolve? How do they potentially get sculpted by planets? What are the masses, temperatures, ages of the coolest dwarfs? How are brown dwarfs similar or dissimilar from planets? And the way we're implementing that is through a series of programs. One, and this cryptic nomenclature you see here, W plus M means wide filters, medium filters, maybe using the GRISM or NIRSpec, and we get some supplementary information with MIRI at longer wavelengths. W means wide filters and NIRSpec, and of course wide M and NB means wide filters, medium, and narrowband. So you have a clue about parts of NIRCam get used. And I'll show examples a little bit on a couple of these topics. I'm not going to go into all of these now, but we're laying a program where we measure the extinction of pre-stellar cores by looking at the transmission through the core of a cloud across the entire NIRCam waveband and correlating that with millimeter wave data from ALMA, and looking at how the extinction also might vary through ice features. We have a program where we're going to be looking at the formation of very massive stars, looking at some of the infrared dark clouds that appear to have proto-stars in them. We have a program of studying young stellar objects. We have a program where we're going to look at embedded clusters, and in particular, this one we want to measure the initial mass function down to Jupiter-sized objects. And then we would also like to observe some Y dwarfs discovered with WISE, some of the coolest dwarfs, and see how the atmospheres of those objects compare to exoplanets. And so here's a picture of the B335 globule, and our program here will be to look for background stars, and we've already done some ground-based pre-survey work where we've used UCURT to find stars at K-band and make certain that we understand their spectral types. And with JWST, we're going to get very clean extinction curves, both in and out of ice features. And we have enough sensitivity that even in something that looks as dense as this, we'll be able to get profiles of extinction as a function of radius in the globule. This shows a nice IRAC color composite map, and that's related to more hydrogen column densities, and where there are these kind of orangish dots are where there may be protostars that we would be investigating using NIRCam. And there's one of the goals here would be to try to assess theories of high mass star formation and the role of fragmentation in that process. The embedded cluster program will use color diagrams such as you see here to separate foreground stars from cool low mass objects, and we'd like to get the initial mass function out of data such as this, and we are wondering whether or not one can distinguish very low mass brown dwarfs from ejected planets, potentially using C/O ratios. And although we won't do follow-up, but once we've established some mapping and cluster surveys in our first epoch, what one would think of as first epoch of data, then other observers, GEOs, can come along later and look for proper motions, look for variability, do a lot of other programs using the same data set.
Hey, Marcia,
Yeah.
I lose you again.
Yeah. I try to keep close to it here.
Thank you, sorry.
That's right. So we come to the Exoplanet Debris Disk and Solar System program. And right off the top, I want to say that we're not looking at how to discover exoplanets or debris disks, but rather we want to characterize known objects. We don't have enough time to do anything that would approach a survey, so we're going to concentrate on doing small samples of interesting objects, and I'll show what I mean by interesting objects in a couple of minutes. And I've already highlighted some of the features that NIRCam has that makes these programs possible, and I'll show a little bit more about the GRISMs in a moment. And when it comes to exoplanet transits, there's a very interesting characteristic of NIRCam with its dichroic. We can read out the short wavelength side at the same time that we're using a long wavelength GRISM, and consequently we can either use that to monitor pointing jitter or potentially monitor star spots, and possibly to take a spectrum using the DHS. And so NIRCam may be quite flexible for doing transit work. So I got to use my other thingy here. So our program in this area is subdivided into 5 different projects, all related in one way or another, as we're trying to figure out how can we learn the most about exoplanets. So there's Coronagraphic Imaging, where we'll do direct imaging of planets. This will also tell us something about the architecture of systems, and one of our programs includes a component to discover maybe dimmer planets than have been seen in a known system. There's a program of coronagraphic imaging of debris disks, and here we like to see if there's evidence for ices, and obviously evidence for shepherding or sculpting planets. We have a survey of young M stars to look for planets at or beyond the CO ice line. We have a program to actually take some of the known systems known from ground-based AO work and actually take a planet or two that are separated enough from the parent star and just get a direct spectrum with NIRSpec. There are a few cases where that may be possible. And then a big program of transit spectroscopy. And lastly, a program to look at a carefully selected sample of KBOs and trans-Neptunian objects, and to see how some of those, the ices on some of those objects may or may not compare with what we see in exosolar systems. So the coronagraphic imaging is, at the moment, we're thinking of a survey where we would use these filters, and also these would be, this selection of filters would be to characterize the planets that are already known in the systems, and then two-band, wide-band deep imaging to look for lower mass planets, and 2 filters so that one can reject background objects. And this graph shows a collection of models computed by Carolyn Morley and friends, and these are different, temperature exoplanets, and you can see how the NIRCam medium band filter suite will not give a complete spectrum, obviously, but give one a good handle on matching to these models. This dotted line through here is the NIRSpec sensitivity in 10 to the 5th seconds. And so one is not going to use NIRSpec on a lot of these cool brown dwarfs or exoplanets. And so that's where this NIRCam filter photometry will help a lot because of the relative faintness of the objects. Here's a sample of a possible coronagraphic observation of GJ504, G0 star not too far away, and there's a known 4M Jupiter planet 2.4 arc seconds from the parent star. This was discovered in some Subaru work. And here's a suite of filters that we would use, and the signal to noise that we would get in 800 seconds using these filters for planets at various separations, and of course what's shown is in red is for the planet that's known, and then the two wider filters we would be trying to find lower planets, and you can see the relative sensitivities, and the W filters we would go significantly longer. We talk a little bit about the long wavelength GRISMs. They were originally envisioned as a backup scheme to the dispersed Hartmann sensor in case segments ended up too far apart for the dispersed Hartmann sensor to get an adequate spectrum to pull them to measure focus difference. It's now thought that's very unlikely, but we still have these nice GRISMs in our long wavelength arm. There are 2 GRISMs per arm, one aligned to rows, one aligned to columns. So they're slit GRISMs, and there are a couple of Spectra you can see in the upper left corner here from some of our test data at Goddard. This dropout in the 4.3 micron filter is actually due to carbon dioxide ice in the telescope simulator. So indeed, this filter detects carbon dioxide ice. This shows how long the spectrum is for one of the W filters, and this arrow shows the length of a spectrum if you use our widest long wavelength filter, which let you cover from 2.4 to 4 microns in one exposure. And if you want to cover the entire 2.4 to 5 micron region, you have to use 2 filters. So it would take 2 transits for that. The graph here shows the saturation limits. What bright star can we study using these GRISMs? And you can see that we can, in the long wavelength arm, we can measure stars of 3rd to 4th magnitude. So although JWST is a huge telescope and we can't read out as rapidly as one might like, we still can do a pretty good job. And I should mention that these saturation limits assume something that we call stripe mode. The NIRCam detectors can be read using subarrays, and usually a subarray goes out just one of the 4 detector outputs. But if you orient things correctly, you can use the 4 outputs and read out the full width of the array, the full 2048, but only a selected number of rows. And so these limits are derived assuming that you read out the full 2048 width, but maybe only 64 pixels in the vertical direction, so that you have plenty of sampling to not worry about pseudo slit losses, shall we say, but can still observe very bright stars. Unfortunately, NIRSpec doesn't have this stripe mode for reasons that were good at the time, and I'll let them explain that later. NIRSpec does have a large square aperture that may be very interesting to use for transits. And whether NIRCam or NIRSpec is going to yield the very best results, I think we won't know till we're on orbit. So our transit program is, we're thinking of characterizing of order 5 planets chosen from to cover a suite of possibilities, and we're also not looking to do any phase curves. We don't think in the time that we will have available and how early in the mission we have to observe that we're going to understand the behavior of the telescope well enough to try to go for a full-blown phase curve. That will be left for others. I also mentioned a paper that Chaz Beichman led that was the result of a meeting held right there at IPAC on JWST transits covering all of the instruments, not just NIRCam. So our program, this is sort of the 4 categories of kinds of planets we might choose from. And Tom Green and Michael Line and others have computed a variety of simulated transit spectra. These plots, which are now in press, are for one transit, and you can see that if an object is not cloudy, then one is going to want to use short wavelengths to look for these strong features. But as we know from HST, there are cloudy objects and you don't see so much. It's what you would get for some emission spectra. And the target selection is going to be something we spend a lot of time thinking about. And M Line, in this case, is Mike Line, who has been at UC Santa Cruz and will now be moving to Arizona State University. And he has developed a program where you can model exoplanet and vary the composition of the atmosphere and produce synthetic spectra and check what features can be used, what wavelength regimes can be used to best effect to recover what the constituents of the atmosphere are. And here's a possible source list that we might use, but I have to emphasize we haven't made any final choices yet, because one can always hope that K2 will discover the Goldilocks planet. I've already mentioned this possibility of doing simultaneous short wavelength transit observations, and here's an indication of if a planet covers a star spot, that can cause variations, and that if you don't have high enough signal to noise, you might not understand what you're seeing in the long wavelength arm, and we could monitor this and at short wavelengths at the same time we get the long wavelength spectrum. And a mode that's much more speculative would be to take the output of the dispersed Hartmann sensor from short wavelength data while simultaneously getting long wavelength GRISM data. But right now, this is not an approved mode in the Institute's accounting of things. And I'm hoping that we will be able to try this during in-orbit checkout and get this moving so that eventually it will be available so that one could get simultaneously short wavelength and long wavelength spectra in a transit. So I'll just summarize by saying that NIRCam has been obviously designed to preserve JWST's diffraction limit and to use its big cold primary mirror to good effect. And I've discussed some of our team science programs, but there's going to be an awful lot left for everybody else. So thanks for listening, and I hope my voice didn't drop out too badly.
Thanks, Marcia. That was great, all the detail you provided about your thinking on what you're thinking about for the GTO program. How many questions?
Before we get started, I have one quick reminder. All of Marcia's slides are available on a website. You should have the link to that from the announcement. There's also recording. It also gives the schedule for the upcoming talks. Next upcoming talk will be on your spec. And if you are online and you'd like to ask a question, either shoot me an email or so that I can call on you, or type your question into the text box via that WebEx interface.
Okay, any questions? Lynn?
Also, can I ask a question? Survey for the extragalactic part. You quoted a number for 220 hours, something like that. Is that mostly for imaging, or that's and the GRISM?
original number included both imaging and some near-spec follow-up, and we've restructured the program now so that it will be, our time will be paying just for imaging. And if we do 4 times 75 kiloseconds in 2 fields, that's actually less than the total that was shown in that original chart. The NIRCam team would also like us to do a shallow survey. So my guess is that we may, in the end, get closer to that original total of 220 hours, but by virtue of this collaboration with the NIRCam team, I may shift some time from extragalactic to exoplanets.
Other group? Got any? Okay, more questions. Thank you very much, Marcia. We really appreciate your time and the details, and yeah, we're all aware that people are actually really starting to get JWST on their radar. Here, we're starting to get EDT proposals regularly. People are thinking about their ERS program. So, yeah. Yeah, it's finally consciousness that people are really starting to think in details about their program. Okay, and what month? It's the new month. Yeah, day of the month. Yeah. Third day would be on like.
The next talk will be a NIRCam talk by the guys here for Rieke. And it's like March 19th, maybe? I don't remember. It's the third Tuesday of the month.
Third Tuesday. It's the 15th. Is the we get the just the first on Tuesday. Yeah. Okay. And we'll bring them in this room. So great. Thanks, Marcia.
Thank you. Bye-bye.